My dear friends, my dear Sarkar, today I will discuss with you about grand canonical distribution function, system, and heat path approach. I'll derive the expression of grand canonical distribution function, with the help of system and heat path approach. Well, while in going from microcanonical to the canonical ensembles, the constraints of completely isolation. There was a constraint in case of the microcanonical ensemble, and that constraint was complete isolation. Now, this constraint is relaxed in case of canonical ensemble. So canonical ensemble, it allows the exchange of energy with the surrounding. Canonical ensemble, it allows the exchange of energy with the surrounding to keep the temperature constant. And with the results, the E becomes a variable in case of the canonical ensemble because there is an exchange of energy. And such a system, it is called the closed system. Now, there's a further relaxation. The relaxation from the constraint is given while going from canonical to the grand canonical. Further relaxation is given so as to the exchange of particle become possible, right? Exchange of particle or the exchange of the matter, that becomes possible in case of the grand canonical ensemble. So in case of grand canonical, exchange of matter, exchange of energy, both are possible. And with the result now, there are the two variables, the number of particles as well as the energy. So going from canonical to the grand canonical, the n also becomes a variable. In canonical, E was the variable. Now in case of grand, now E and n both are variable. So it is an open system. In equilibrium, the system has the average energy in equilibrium, because system is having the permeable walls with the heat bath or the reservoir. So equilibrium is reached. In equilibrium, the system has an average energy because there is no exchange of energy. But in the equilibrium state, the system having the average energy E and average number of particles N. Remember, it is grand canonical, so that's why E and N both are the variables. But when the equilibrium state is reached, there will be average energy E and the average number of particles. So such a system which is under consideration, it is a grand canonical ensemble. The system is having now the condition of grand canonical ensemble is maybe there is an exchange of energy, maybe there is an exchange of the matter or the number of particles, but the main condition is temperature and chemical potential. It remains the constant. Chemical potential mu and temperature remains constant throughout the process, or with the time there is no change. No change takes place with T and mu, okay, for a given volume V, with the surrounding or with the reservoir. Now we are going to we are going for the derivation of grand partition function. So we take, a system, we call the system as A. This A system, and you put it in a heat path. This is heat path. We are calling the heat path as A dash. What is our system? What is the system is? Now we are having a system A. This is a system A, and it is put in a heat path. Heat path is our surrounding, and we call the heat path as A dash. So we are having two things, a system A and an heat path A dash. And total is the new system which is formed now. It is AT. AT is the sum of A and A dash. And this total new system is isolated from anything else. Okay, so that's there. Whatever is the inside the new system, it remains. Mean conservation of energy or conservation of the number of particles will be true inside the new system. So the system is such that it is allowed to exchange both the energy and particles. Okay, and keeping system and heat path in equilibrium at a common temperature T and common chemical potential mu. This is very important, that mu and T, they becomes constant. So how they becomes constant? Because the system is allowed to exchange both the energy as well as the particles. So at any instant, energy of the system is E and energy of the heat path is E dash. Temperature T is the same, and mu, they are different. Mu is also the same, mu is same, T is same. Okay, so again, this is our system A, energy E, mu and T, and number of particle N. This is a heat path, energy E dash, energy E dash, It may be different from E, no problem. N dash different from N, okay. But T is the same, mu is the same. So this is over the heat bath. So heat bath is very, very large and having very large heat capacity or the thermal capacity. Our common system is AT, which is A plus A dash. Together means the new system is isolated from any other. So at any time, so at any time, time of the system, because there is a exchange of energies going on, and we're thinking that the exchange of energy takes place. So at any time, A has energy ER, okay, and number of particles mean the system A having NR, while the heat bath A dash having energy ER dash and number of particles NR dash. Total energy, because energy conservation, and total number of particles, they remain constant. NT is the sum of NR plus NR dash, and it is ER plus ER dash. You may take the symbol for ES, no problem. ES plus ES dash is equals to ET. NR plus NR dash is NT. Since heat bath is very, very large, therefore, ES, as heat bath is very large and very large heat capacity, ES will be very small in system energy as compared to the total energy, as well as NR will be very, very small as compared to the total NT. So consider, equation 1, 2. So dividing each term by ET, so it becomes ES over ET is like this. And this will be because ES over ET, ES is very small as compared to ET. So it is less than 1. Similarly, NR over NT will be less than 1. Because the heat bath is very large. Now this is very important. Now we are going to define the number of states compatible to it. Compatible to it means to the heat reservoir with energy ES dash and particles NR dash. Okay, we are talking about the reservoir and number of states. Number of states denoted by omega dash. So omega dash is a function of number of states. The function of what? Energy and particles mean ES dash and nr dash. So omega dash means number of states. So because the heat bath is very large and very large heat capacity, so number of states will also be very large. I mean omega dash value will be very large. And if it is very large, it will be independent of the nature of the reservoir. So larger the number of states available to the reservoir, larger will be the probability of it assuming to have the energy Es dash and having particle nr dash. And also it implies that the system which is immersed in the heat bath also assuming energy Es and having number of particles nr. So as per the principle of equal priori probability, in the different microstates, they are having the probability of equally likely to occur. Okay, so the probability P of a system E occurring with the energy Es and number of particles nr is proportional to what? Number of the microstates which the reservoir has. And you know very well the number of states are omega dash. It is the function of Es dash and nr dash. So probability of the system, our system is E, occurring with energy Es and number of particles nr proportional to the states of the reservoir. Okay, and states are omega dash. So we're writing here the probability SR. SR means probability of the system with energy S and with number of particles, nr. So it is proportional to omega dash. You know very well the conservation law. The Es dash may be written as Et minus Es, nr dash may be written as Nt minus nr. As it is Es plus Es dash, Nt is nr plus nr dash. So probability of our system is proportional to omega dash, number of states of the reservoir. Now Es is very, very small if you compare it with the total energy. So, and also the number of particles nr is also very small as compared to the total particles. So keeping in mind the two approximations. Now we are going to take the logarithm. Okay. Why are we taking the logarithm? Because the value of omega dash is very large. Okay. And it varies very rapidly. So it is better writing in logarithm, in the log. So log of omega dash is equals to, this is of the, you know what, reservoir. Omega dash means number of states of the heat bath. It is equals to total states. Okay, omega dash of ET and NT. You know, this factor will be less than this. This is the total. This is only of the heat bath. So exactly because this is of the heat bath states. This is of the states which relates to the total energy and total number of particles. Because there is an equal sign, so there is some subtraction from this term. First of all, how the states are changing with respect to E dash and multiplied by system energy, and how the states are changing with respect to N dash. N dash means number of particles in the heat bath, and multiplied by the number of particles of the system. Then left hand and right hand becomes equal. Okay, this is only of the heat bath, this is of the total, and certain subtractions. Okay, now from statistics we know that this, you go to please go through the statistics first of all. If you don't know the value of these terms, like here, this is from statistics. Currently, by partial differentiation of log of omega dash with respect to E dash is beta dash. We call it beta dash. And remember that beta dash is 1 over Boltzmann constant into the T dash. Okay. And beta dash is, you know what it is? 1 over Kb into T dash. But at equilibrium, what happens? The temperature is the same. Temperature comes to be at the same level in T, not T dash. T dash becomes T. Similarly, partial differentiation of log of omega dash with respect to N dash. We call it alpha dash. Alpha dash is the minus of thermodynamic potential mu dash upon Kb into T dash, because it is with the heat bath. This parameter of the heat bath. But in equilibrium, mu dash attains the same value as mu. Mu is the same for system and heat bath. T dash also becomes T. But keep in mind, alpha is with negative value. Alpha is minus of this and beta is okay, it is this. Now we are substituting this value, okay, we are at here, right, into ES, and we are substituting this value where here. So this factor, it relates to the total. The total states, they are the constants. This is not varying. So we call it this term as constant. And substituting the values, so it becomes constant minus beta ES. This is negative sign. Okay. Here it is the minus negative sign. This is minus sign. This is again a negative sign is here. Minus beta ES minus alpha NR. Now omega dash again number of states of the reservoir. Because the probability of the system, it is proportional to the states of the heat bath. So it is proportional to probability is proportional to the number of states. And okay, what we are doing, taking the anti-log to both the sides. Anti-logarithm becomes exponential. Okay, when you take the anti-log of log, that only left omega dash. And probability is proportional to, probability of the system is proportional to omega dash. So again, taking here the anti-log means exponential e raised to power. Power what? This minus beta ES minus alpha NR. And taking minus beta as constant. Minus beta outside the bracket. And what left inside? Okay, because minus beta is taken outside. Here it becomes alpha over beta because previously there was negative sign. And negative sign is taken common. Taken as common. But what is alpha? Alpha is alpha and beta. Alpha and beta, they are related with mu. Alpha is equals to minus mu times the beta. Alpha is minus mu times the beta. So it becomes, since sum of all the probabilities must sum to 1. So now we are applying the normalizing condition with summation. Normalizing condition with the summation. Now looking here the probability was proportional. Now here it is equal. Okay, this is the difference. So that's why we are dividing by the total. Okay, the total number of the states. So there was the proportional sign. Now it becomes the exactly equal, the probability of a system with energy S and number of particles R is equals to, so this is called the grand canonical distribution function. I think it is clear, because for understanding, a complete knowledge of statistics is required, because I substituted here some value which is from statistics. So it is my advice, please go through statistics first, then you will understand properly grand statistical distribution function. Okay, and this is the last distribution function of grand canonical. Thank you.